Right. Next one.
Good morning to all present. We are Group 5 and today we'll be presenting about the potential of gene therapy to improve cancer treatment. So my name is Celeste and I'll be giving you a brief introduction to gene therapy. So gene therapy is defined as the introduction of genetic sequences into cells of living organisms which results in an alteration of cells or tissue function in a manner that corrects or treats a pathological process. So this may be accomplished through the transient or permanent transfer and integration of genetic material into the host genome. So this genetic material that is transferred may encode for a complete therapeutic gene that corrects a defective function, coding sequences for products which interfere with pathological function, or even to enhance normal cellular function to achieve a therapeutic effect. So gene therapy is typically applied to somatic cells. So in the ex vivo method, the genetic material is introduced into the cells that are extracted from the patient. The cells are then reintroduced into the patient as a homologous cell transfer. So genetic material may also be introduced directly into the patient cells in the in vivo method. So gene therapy has a great potential to be developed into treatment options for diseases such as cancer, immunodeficiencies, hemophilia, and cystic fibrosis. Researches that are currently underway include the gene transfer, p53 gene transfer to stop tumor growth in lung cancer, and the CFTR gene transfer to manage cystic fibrosis. So the focus of our presentation today will be somatic cell gene therapy as a cure for cancer, using a chimeric antigen receptor, or better known as CAR, T-cell therapy as an example. I'll now pass the floor to Wandi.
Hi, I'm Wandi. So I will now talk about the concept of gene therapy. So I will start with the somatic gene therapy concept. So basically, somatic gene therapy is about the transfer of desired gene into the somatic cells of a patient. For example of the somatic cells are like immune cells, bone marrow cells, muscle cells, and other cells that you see in the body, except the reproductive cell. So in this somatic gene therapy, the reproductive cell will not be used, and also the modified somatic cells will not pass on, will not be inherited by the next generation of the patient. So our main focus for today's presentation, the CAR T-cell therapy, is an example of this somatic gene therapy. Okay, the CAR T-cell gene therapy. So in order to know more about the CAR T-cell gene therapy, we have a question about this. What is CAR T-cell? So CAR T-cell actually is a modified T-cell which has chimeric antigen receptor, the CARs, and then it has, and this type of CAR T-cell, it has 3 different generations, first, second, and third generations. Okay, so you can see that I did mention about the CAR T meso cells. So because by referring to the case study given by Dr. Sharina, we will use these CAR T meso cells instead of using another type of CAR T cells. Okay, so what's the specificity of the CAR T meso cells? So this CAR T meso cells is actually designed to target only the mesothelin antigen, which can be found in the tumor cell and cancer cells. Okay. So the next question is, what is chimeric antigen receptors, the CARs? So these receptors, it have binding domain, the SCFE, transmembrane domain, and also intracellular signaling domain, the CD3, CD28, or the 4-1BE. So by having these receptors on the T cell, it enables the T cells to be more easily to recognize the targeted antigens such as mesothelin, just like I mentioned just now, and also it helps to fully activate the functions of T cell. So this shows the 3 different generations of the CAR T cells. So which generation do you think is most difficult? Which generation do most
Answer
people.
chocolate.
Answer for sugar. Never mind, it's okay. Just guess a name. Which one is the most preferred one? Let's go. Never mind. Go ahead. Actually, it's a second generation car is the most preferred one. Why? Because the first generation car, you cannot activate the T cells because of the lack of co-stimulation domain. Alright. So for the third generation car, although it has two co-stimulation domains, but then it will cause toxicity in patient's body. Alright. Such as the inflammation reaction may happen. So it's not good to use the third generation car. So we most prefer is the second generation car, which has only one co-stimulation domain. And it will not cause toxicity also. Okay, so next. Okay, now let's tell how to form a CAR T cell. Okay, so first we will extract the T cell from a patient through a process known as leukapheresis. Leukapheresis is the method which extracts only the white blood cell from the human body. Okay, so next. The CAR's coding sequence, which is in mRNA form, will be introduced into the extracted T cell through the lentiviral method. Okay, a lentivirus will then fuse with the cell membrane of the T cell, and then the mRNA coding sequence, which consists in the lentivirus, will be released into the T cell and undergo reverse transcription to form DNA. Okay, so the DNA sequence of the CARs will integrate itself into the genome of the T cell and undergo the transcription, and for the transcription process, a complete chimeric antigen receptor will form, and then it will insert itself in the cell membrane of the T cell. So now a complete successful CAR T cells form. Okay, how does the CAR T cell works? So next, so let's see from here. This SCFE is the binding domain, which will bind to the antigen. And in our case, the antigen will be the mesothelin. Okay, so the SCFE will bind to the mesothelin, and then it will then activate the T cell to send to release apoptotic signals. So do you have any idea what is apoptotic? You want to do search and not can also? Can you Google search, then you can get the answer also? No, it's okay. So apoptotic actually derived from the word apoptosis. Okay, apoptosis means the process of cell death. Okay, so by releasing these signals, it will initiate the release of cytokines, and then causing the proliferation to happen in the patient's body. Okay? So through the proliferation, the cytokine will activate other immune cells to work together to kill the tumor cells. So this example, cytotoxin, it will activate the cytotoxic T cell, okay, to release conforming granzyme and FSSL, and then it will activate system of this, which is the cascade, which is needed for the process of cell death to release and activate. Okay, so the cascade will cleave a part of the protein of the cellular protein of the tumor cells, and without the cellular protein, the tumor cells cannot survive and will die. So I'll pass to my friend Gayatri.
Hi, I'm Gayatri, and I'm going to talk about efficacy in gene therapy. So, what is efficacy? Is the ability of a treatment to produce the desired therapeutic effect under a controlled condition. So, the gold standard for checking efficacy in treatment is the randomized clinical trial, which is the RCT stated there. A reason for that is because it minimizes variability in the trial. Okay, so for example, we use to check the purpose of the study is to determine a safe number of these cells to infuse and to see if these tumor fighting cells cause metastatic cancer tumors to shrink, which is the same one in the CAR T cell therapy which was given. So as you can see, we have some exclusion and inclusion categories. So moving on, so there are actually many factors that affect efficacy in gene therapy, but I'll only explain these two in terms of general gene therapy. Okay, so for the first problem is that we have issues integrating therapeutic DNA into the genome. And secondly, they want a cell that contains a DNA that is stable and has a long life. Why do we want that? It's because we want it to last for a long time, and we want it to not only attack the human cells, but also to prevent it from happening in the future. And if it isn't stable or long-lived, it may require multiple rounds of gene therapy, which will be a problem. Firstly, because it's very expensive. Secondly, it's due to immune response. Anything you put in your body maybe is a foreign substance, and you see and your body is going to attack it. Okay, so it's okay that it produces immune response because there are methods to sort of decrease it and allow the patient to have this in a safe way. But the problem is, once you have the immune response the first time, the patient's T memory cells will remember this as an antigen, and the next time you want to put the second round of gene therapy, the body is programmed to straight away kill the treatment, so it will increase the efficacy of the treatment. Okay, so next I will go on to factors affecting efficacy in CAR T-cell therapy, which is our main topic. So the first thing that is affecting it is co-infiltration of T lymphocytes into solid tumors. So why is that? Because, okay, so solid tumors, compared to normal cells, have high concentration of blood vessels due to angiogenesis, which is a process we use to obtain more oxygen and nutrients. Secondly, it has extensive vascular leakage, wide gap of vessel wall clearance, poor lymphatic drainage, which increases the interstitial fluid pressure. And ultimately, this results in enhanced permeability and retention effects of lipid particles and macromolecular substance within these solid tumors. Okay, so let's take a trip to tumor microenvironment. So this is basically what I explained previously. So you can see that there's like a lot of space in between. So this is where the lipid molecules will actually flow through, and this will increase the pressure within it. So the T cells that are delivering to it will have a more difficult approach to get into the tumor cells. But scientists actually turn this into a positive thing in nanoparticles, nanotechnology. They use lipid molecules such as liposomes to deliver the drug to deliver the T cells to the tumor cells, because the liposomes are lipids, so they will be able to not only permeate the cells easily, but they can stay there for a longer time, which increases efficacy. But it's not applicable in our current research. Secondly, is immunosuppressive environment. There's many reasons why the tumor produces an immunosuppressive environment. Firstly, is due to hypoxia, which is an oxygen deficiency. So this is because as the mast cells produce, it moves further away from the blood supply, and because of this, it's less ideal for T cell growth, the one that you are actually sending in, the one that you're sending in. And because of that, the tumor cells tend to undergo aerobic lipolysis and produce lactic acid, which you know is going to decrease the surrounding, and this will not be good in terms of the T cell growth, the CAR T cell growth. Thirdly, is inhibitory effects of tumor-derived cytokines. So the thing about cytokines is that they are immunomodulatory, which means that they may induce or repress tumorigenesis. So later on, you can see how they actually use cytokines to repress tumorigenesis. Okay, so this is the article that we found from the National Cancer Institute website. Okay, so they say that the EPR effect of solid tumor plus the suppressive nature of tumor microenvironment is going to impede the infiltration into tumor tissues. So actually, action taken to improve efficacy. So firstly, they incorporate cytokines or chemokines. Why did they do that? Because it enhances the infiltration of T cells and recruit other immune effectors. And they do this by modulating the tumor stroma to release more cytokines such as interleukin-2. And this further activates innate immune cells response to tumor cells. So it's very useful to use this because CAR T cells may not be able to see all the tumors, but the cytokines are able to help with that, to see the inaccessible, for example, to see the inaccessible tumor lesions. Secondly, is optimization of culture conditions. It is said that the best number of days to carry out the culture is for 10 days. Secondly, we add cytokines such as IL-2 to enhance T cell expansion. But once you want to put it into the in vivo or in vitro, you put IL-7 and IL-15 because they have more sustained expansion and better chance of survival, which will increase the efficacy of the treatment. Next, we have to modify CAR to better target tumor-associated antigens by integrating co-stimulatory signals, CD8 plus, which is a transmembrane glycoprotein addition molecule, and this enhances activation of T cells. This is because they have very high affinity to the alpha subunit of major histocompatibility complex protein. And this gives the cytotoxic T cells and the target cell bound closely together during the antigen-specific activation. Last but not least is by combining with other treatments such as LD15 and fludarabine, which will eliminate tumor cells more thoroughly, but Xiaowen will explain further on that.
I will talk about the side effects of the CAR T cell treatment. So the first side effect is cytokine-release syndrome, also short-term CRS. A defined marker for CRT-induced CRS is increase in serum C-reactive protein. There is a reflecting a strong correlation between CRP and cytokine level. As you can see from this graph, as the cytokine level increase at the same time, the CRP and ferritins also increase. For information, these two are classified as acute phase reactants, which means that they will increase in their level in response to inflammatory. So CRP can use in rapid clinic diagnostic. Second, insertional urgency. When the process that insert the mRNA, there's something went wrong, so it will cause a vector induced immortalizations and lead to uncontrolled clonal expansions of T cell. However, the risk is very low. Neurological toxicity. This is cause confusion, delirium, aphasia, seizures. However, the conditions can be reversible and the cognitive pathophysiology is unknown. Next, on target of tumor toxicity. We want the CRT cells work in this way, target on the mesothelin on the malignant T cells, B cells for example, and kill the tumor cells. But the normal B cell also express the mesothelin, so it will bind on the mesothelins of the normal B cells and cause the B cell aplasia and will cause death. Lastly, anaphylaxis or allergies, immune response to mouse derived or recombinant proteins. This also can cause the cardiac respiratory failure. Now the management of the toxicity. Number one, pharmacological immune suppression in CRS. We can use tocilizumab or systemic corticosteroid. However, the prolonged use of corticosteroids may reduce the efficacy of the CRT cells. Number two, suicide genes. The products will activate the suicide genes product to kill the cell itself. Elimination genes. The modified cell can be programmed to express a non-surface antigens that may cause the cell death, triggered by infusions of the associated antibodies. more target activations. This require identifications of two target antigens with core expressions on the malignant tissue of the CRT cells. For CRT cell activations, this can reduce the on-target off tumor toxicity because the normal cell only have one target antigen. So in case of B-cell aplasia, they require immunoglobulin replacement to prevent the further infections. We also can use the lowering the dose or multiple low dose. Last but not least, intensive care and strict monitoring is required. Now I'll pass to Jawan.
Okay, so I'm Jawan. I'll talk about implementation of gene therapy in clinical setting. So it can be used to treat genetic disorders, mostly single gene mutations. For example, cystic fibrosis, where there is a mutation on the CDFR gene on chromosome 7, and X-linked SCID, bubble boy disease. That's what we call because SCID stands for severe combined immunodeficiency. So the child due to this, they have immunodeficiency, and their immune system is very low, very weak. So they live in a plastic shield. There's a boy in Europe in plastic shield to protect from infection. So we call bubble boy. And then hemophilia, gene encoding for enzyme factor A. There's a mutation there, so it causes hemophilia. And Huntington's disease, where there's a mutation on the Huntington gene. And Duchenne muscular dystrophy, where there is a large deletion or insertion of dystrophin gene. So we have very weak muscles. And other disease, for example, Alzheimer's. So to treat this, they actually use gene therapy to introduce neuroprotective factor or nerve growth factor so that we can prevent the loss of cholinergic receptors. And then cancer, we correct the mutated p53 gene or we target mesothelin as in the question. And atherosclerosis, we introduce vascular endothelial growth factor, VEGF. This is very interesting because in our country, when people get a blocked blood vessel near the heart due to atherosclerosis, they actually do a bypass surgery. So they take a blood vessel from another part of your body and you link to your heart so you can bypass the blocked part. So by doing this, they actually can, it's called bio bypass, where the body will actually grow its own blood vessel to bypass that part, angiogenesis. So I think this is there's a very high possibility in Malaysia in the future because we have very high rate of cardiovascular disease and Parkinson's disease. So the first gene therapy approved by the European regulator is Glivera. It's developed by a Dutch biotech firm called Unicure, and it's launched in Germany early 2015, last year. So it's used to treat lipoprotein lipase deficiency. So what is lipoprotein lipase? Sharon, what is lipoprotein lipase? PSE. So pay attention. Sorry, no harm intended. So it's an enzyme because if we don't have this enzyme, we cannot break down lipoprotein. So fat is built up in the blood, leading to cardiovascular disease, for example, atherosclerosis. So this therapy is actually a virus of clear liquid. So it consists of engineered copy of human RPL genes packaged in tissue-specific chromatin in a non-replicating AAV1 vector. So it has a particular affinity for muscle cells. Why? Because this enzyme is mainly produced in skeletal muscles and adipose tissues. So normal LPL gene is introduced to the cell and your body can now produce functioning LPL. So an average patient will need around 19 vials of Glivera. So each vial costs around 44,000 euros. So you can expect how expensive this treatment is. So even there is gene therapy, can you afford it? So that's one thing to think about. And Shrivelli, this is the first gene therapy approved by the European regulator for children for what I said just now, the AAI SCID, a kind of SCID. So this is the first ex vivo stem cell gene therapy. It's developed by GSK. Everyone knows what GSK, right? It's very popular, famous. So ADA is caused by ABSSDIE. It's caused by a faulty gene inherited. So the production of adenosine deaminase is prevented. And this protein is required to produce lymphocytes. And so they remove the stem cells and correct it and put it back. So you can see there's some partial remission, but not total partial remission, because it only shrinks the cancer cell, but not completely removed. So if it's total remission, you cannot detect any more cancer cells. And then this is the example. You can see because you can't just use CAR T cells, so you use some complementary medicine. We learned before nitrogen mustard, interleukin, a kind of cytokine, and fludarabine is anti-E metabolite. I'll pass the word to Sarah.
Yes, let's begin here. Yes. Okay, so there is no doubt that gene therapy represents a significant progress in the advancement of medical technology. And as any
Yeah, just
okay,
Just go to the
so I just ignore this.
So because of there's a lot of ethical issues, so gene therapy, yes or no? Does the advantage outweigh the disadvantage? Disadvantage, for example, ethical issues and the cost of it is very expensive. So the decision vary in different cases, but mostly they use it as a last resort. For example, the case of Emily Whitehead, she has leukemia when she was 6 in 2010. So she's now in remission for 4 years. After receiving CAR T cell gene therapy. So it's very inspirational. And there's a QR code here. After that, you can go check online if you are interested. It's very inspirational. These are references. And okay, next question.
questions?
So, taking into consideration all the, I don't know if you did not present the ethical issues, but you know what are the ethical issues. So, taking into consideration the ethical issues, the cost, the efficacy, what do you think of gene therapy? How far we are from implementing gene therapy in medical setting? Just a general opinion.
I think there's still a gap since the first approved has just been launched in the Europe area last year and this year. And it's very expensive, so most people probably can't afford it. But I've heard some governments they actually put some funding to Glybera. Yeah, and then I think that for string rallies, for example, because most of SCID they affect children first, because it's inherited. So a lot of babies die because their immune system is weak. So I think it's very essential that we develop in a way that we can reduce the cost so that more people can afford the therapy. And also there's another option of signing up for clinical trials. For example, Emily Whitehead, her parents actually thought that going for clinical trial for CAR T cell is at least they're trying something else instead of being hopeless and wait to die. So, and by signing up for clinical trials, it's free. So you get to be treated, and if you die also, at least you can give some extra information for future patients so that they have a better chance of survival.
So another thing about the VEGF, you mentioned something very interesting about VEGF. So that one has been successfully implemented somewhere else, or still under trial?
It's still under clinical trial, but if they actually succeed in developing this technique, I think it will really benefit Malaysians.
I just have one question for Gayatri.
you mentioned about, I can't remember which slide was it, but it's about Arabic in low pH condition undergoes aerobic glycolysis. Can you go back to it? After this. Yes.
No.
No. Right.
This one, yes.
Yes. Can you? Do you think the information is incorrect? The low pH undergo aerobic glycolysis.
Oh, sorry, it's wrong. Sorry.
What is wrong?
Supposed to be aerobic. Sorry.
That's all. Thank you very much. We're done. So thank you all very much for this session.